Let's get started. So our next section will be introductions to CKKS. Yong-Soo is the author of that paper, and he's the S. And welcome, Yong-Soo. And this is not something like a lunch talk. It will be more technical, and I think you should pay attention to that. Thank you.
Thank you, Wei, for the introduction. Hi, everyone. Good afternoon. I give a brief tutorial on CKKS, and which is one of two homomorphic encryption schemes supported by the Microsoft C library. And please feel free to interrupt if you have any questions anytime. So HE technology basically brings the plain computation to the encrypted world. So most of the homomorphic encryption schemes, including BGV or BFV, support discrete computation, as explained in previous session, such as Boolean arithmetic or integer arithmetic or modulo P operations. But in practice, we also use some other variable types, such as double, to take some advantage of approximate computation. And the CKKS natively support encrypted approximate arithmetic. So basically, this scheme was designed in 2017, and back then it was initially called HAN by the authors, but nowadays it is formally called CKKS after the author's name to distinguish the name of this scheme from the name of public libraries which implemented the same scheme. So there has been a sequence of researches improving the functionality and efficiency of this CKKS scheme, and I give some high-level idea about algorithms and API of C library in the CKKS mode so that you can play with it later without checking all the details of these papers. And the primary goal of this talk would be to understand this example code in the C library. You can, if you have installed the C library, then you can just open this GPP file if you want. This code basically evaluates cubic polynomials and multiple real numbers. And another goal is to learn some important concepts and languages widely used in H community so that we can use this keyword during the bootcamp discussions. So before we get started, let me first record the floating point and fixed point arithmetic because it's sometimes confusing. So in the floating point number system, a real number is represented by a product of an integer called significant and a scaling factor, which is usually represented as a base to the power of a base. And the intuition behind this representation is that the floating point number is not exactly the true value we want to store, but it's just an approximate value which implicitly includes some numerical error after the radix point of this significant. And there are two main methods for multiplication between two floating point numbers. They are called floating point arithmetic and fixed point arithmetic. They are somewhat similar, but both of them first multiply two significant bits and make perform some rounding operation to make trade-off between precision and efficiency. But the main difference is that in the case of floating point arithmetic, we always store a fixed number of bits of significant, and scaling factor can dynamically change during the computation. As you see in this example, all floating point numbers have 6 bits of significant. But in the case of fixed point arithmetic, we keep the same scaling factor, not the bit size of significant, so that the bit size of significant may change. Here, the inputs have 6 bits, but the output significance is 7 bits integer. But scaling factor is stable as 2 to the 5. So in the case of encrypted computation, the fixed point arithmetic is more suitable since we are not able to check the bit size of intermediate values during the computation. So floating point arithmetic is much more tricky. So roughly speaking, CKKS supports a sort of fixed point arithmetic, but with some extra noise from the system. So in this talk, message and plain text will refer to two different variable types. So message would be a vector of floating point numbers or a vector of complex numbers. And it should be first transformed into a plain text via a public encoding map before being encrypted. And the CKKS scheme provides various homomorphic operations such as addition, multiplication, rescale, rotation. Encoding and decoding are public transformation between message and plain text. As noted in previous session, the scheme works over the set of polynomial modulo x to the n plus 1. The set is denoted by R. And for given message, which is a vector of n over 2 complex numbers, we first multiply it by a scaling factor and pack these n over 2 numbers into a single integral polynomial using some Lagrangian interpolation over this ring. You don't have to know all the details, but as a toy example, if you encode this pair of complex numbers with scaling factor 2 to the 7, then you end up with this integral polynomial m. And we can double check that if you evaluate two roots of unity at m, then you recover a kind of approximate values of 2 to the 7 times of the input vectors. So, and later, CKK's scheme will support some parallel computation on these multiple slots. This individual, so you can imagine that a plain text implicitly has some n over 2 plain text slots. Each of them can store a complex number. And after encoding, each of these slots contains some approximate values of delta times zi. And you should use a larger delta to keep more precision because m is basically an integral polynomial. So this encoding algorithm includes some rounding operation. So if you use too small scaling factor, then you lose too much precision, significant bits after radix point. Okay, so in the source code, we first initialize the input vector, which is n over 2 dimensional vector of real numbers between 0 and 1, and use encode function to encode it into a plain text X plane. And we are going to evaluate this cubic polynomial, so we should also encode the coefficient of this polynomial as well. They are pi and 0.4 and 1. It's simply a scalar, so if you encode a pi, then it is mapped to a plain text which contains delta times pi in all of its plain text slots. So we can use the same coefficient for all slots. Okay, so R sub q denotes the residue ring of R modulo q, which is the set of integers, set of integral polynomial modulo x to the n plus 1 with coefficients in z modulo q. So the secret key of CKKS is a polynomial s, and public key or symmetric key encryption of a plain text m is a pair of polynomial c0 and c1, such that c0 plus c1s is approximately equal to m modulo q. So it means that this c0 plus c1s modulo q is the decryption circuit of CKKS system, so that the decryption circuit correctly recovers the plain text m if m is smaller than q. Otherwise, we will have some modulo q reduction in m, and the result would be incorrect. So for simplicity, we often write the ciphertext CT as a linear polynomial C0 plus C1s. And decryption circuit is just substituting S by the secret key, small s. So you can just imagine that you store plain text blocks, n over 2 plain text blocks in larger black boxes of size roughly log q bits. And only SK secret key owner can open this black box. And the size of this black box is parameterized by this important parameter Q. And remember that this encryption algorithm introduced some small noise to ensure the security of HE system. So that C0 plus C1S is not exactly equal to M, but it's just approximately equal to M. So the noise different from the BFV scheme explained in the previous session. In the case of CKKS, we don't distinguish noise from plain text. Noise is considered as a part of a message. It is just considered to be a numerical error during approximate computation. We anyway work on approximate numbers with some error. So if you encrypt 0 and directly decrypt it, then you don't get 0, but just a very small number, which has no upper bound depending on the parameter of HE system. And encryption function is in the line 129 in the source code. And the CKKS scheme supports addition and multiplication between plain text and ciphertext, or ciphertext and ciphertext. First of all, the multiplication between plain and cipher returns a ciphertext of the same black box size, which includes the product of these green plain text blocks inside of it. So you can just compute the multiplication between plain text inside of this black box. And in the case of ciphertext multiplication, it's very similar to the previous case, but a bit more complicated, because if you multiply two ciphertext, then you get the same size black box, which include encrypted product of two plain texts. And record that the plain text or ciphertext is usually written as this linear polynomial. So technically, you just simply multiply two ciphertexts and returns a quadratic polynomial, because it's a product of two linear polynomials. So this homomorphic multiplication is usually followed by another operation called linearization, which transforms this quadratic ciphertext back to the linear ciphertext while almost preserving the encrypted plain text. So roughly speaking, if you perform the composition of homomorphic multiplication and linearization, then it will return a linear ciphertext which encrypt the product of plain text blocks of the two input ciphertexts. So this is the source code. And this procedure requires some extra public parameter called the linearization key. So rescaling is the key operation which makes CKKS have its own characteristic and benefit. So this rescaling operation works just like the rounding operation of fixed point arithmetic. So after homomorphic multiplication, the scaling factor of an encrypted plain text becomes delta squared from delta. So if we repeat homomorphic multiplication, then the scaling factor will grow exponentially as the computation progresses, and the plain text will overflow the size of this black box very quickly. So similar to the case of fixed point arithmetic, the rescaling operation divides the ciphertext by delta and cut off the least significant bits, log delta bits of ciphertext moduli, and thereby plain text. So we recover the scaling factor delta after rescaling procedure. This is why the rescaling procedure usually comes after homomorphic multiplication to maintain the same scaling factor during the computation. Okay, so the ciphertext modulus can decrease during the computation by rescaling. But what would happen if we multiply two ciphertexts with different moduli? In this case, there's no good solution of multiplying two, but we just have to discard some most significant bits of a ciphertext with a larger modulus, so that we make them have same ciphertext modulus before performing homomorphic operation. So as you can see, this is not an ideal situation because we are not fully utilizing the computational capability of a ciphertext. So it is very important to choose the best circuit representation without this unbalanced multiplication, which basically wastes ciphertext modulus. So let's look at the simple example. We just want to compute the product of 4 ciphertext. We can consider 2 different circuit representations of the same function. If we use the first representation, we basically have 3 multiplications, but 2 of them are unbalanced multiplication. So we consume log delta bit 3 times. So final ciphertext modulus would be Q divided by delta to the third. So as you can see in this figure, the overflow could happen if this encrypted plain text is larger than the size of this black box. But in other case, if we use this tree structure, then we finish the computation while consuming only 2 log delta bits of ciphertext modulus, and resulting ciphertext still has a large enough modulus for correct decryption. Okay. So I believe you probably got some intuition why the depth of a circuit is so important feature in HE evaluation. So the HE community formalized this notion and we came up with some keywords like a level. Ciphertext modulus is a product of base modulus Q0 and a power of base scaling vector delta. And we say that a ciphertext has a level L if its ciphertext modulus is Q sub L, which is product of Q0 times delta to the power of L. So this level of ciphertext is a good indicator which effectively presents the computational capability of ciphertext. So the level is decreased by 1, usually after each of the multiplication. And we consume this all L level, and no more arithmetic is allowed when a ciphertext reaches the lowest 0 level. So no more multiplication is allowed for 0 level ciphertext. So we can use this language to explain the functionality of CKKS algorithm easily. So a ciphertext is usually labeled with its level L and scaling factor delta. And you can check how homomorphic operations change this label information of ciphertext. So for example, if you perform rescaling operation on ciphertext, then level is decreased by 1, and the scaling factor becomes to changes to delta from delta square. So, and as you can expect, the cost of encrypted computation heavily depends on the depth of homomorphic encryption system. So when you bring a computational task into an encrypted world, the overhead between this plain computation and encrypted computation is not a constant, but it heavily depends on the depth of circuit. So in general, an optimal algorithm in computational number theory may not be optimal over HE system. So for example, when you train a machine learning model, we usually make the use of gradient descent method. But this is really, really expensive in homomorphically encrypted world because we basically repeat a number of iterations for updating model. And each of iteration will consume at least 1 level. So if you repeat 1,000 iterations, then you should prepare a homomorphic encryption system supporting at least 1,000 level, which is not implementable in practice. Okay, so let's get back to this example of source code and focus on the first term, pi times x cubic. So since it has degree 4, we can evaluate this term with only depth 2 system. by utilizing this tree structure. So we first perform the scaling of ciphertext, followed by linearize and rescaling operation to obtain this encryption of x squared with scaling factor delta. And then we can use plain cipher multiplication algorithm followed by rescaling operation to generate another encryption of pi times x with scaling factor also delta. And finally, we can multiply them to get an encryption of the first term, desired term. This is the source code, and we consume the two level. And the most difficult part of computation is finished, so we should be almost done. But actually, the source code still have more than almost 150 lines left. So in fact, what I have explained so far is slightly different from the algorithms exactly implemented in our algorithm, because there has been a bunch of modifications and improvement on CKKS algorithm for improving its functionality and efficiency. And some of them are not mathematically beautiful or conceptually simple, but we anyway applied some of those optimization techniques to our library for engineering optimizations. So I briefly explained some major issues in implementation of CKKS, but it's fine if you don't understand all the details, because you can still enjoy the power of this CKKS library without knowing all the details. So just understanding its high-level idea is enough. So when you set the parameter for the CKKS system, as I explained, low Q, bit size of the ciphertext modulus should be larger than the product of depth of circuit L and the bit precision of correctness log delta. So it could be several hundred or even larger than 1,000 bits in practice. So obviously, it is very challenging to implement this high precision arithmetic on standard computer system, because we usually work on 64-bit processor, but this homomorphic encryption library require 100-bit arithmetic, modular arithmetic. So one well-known solution for this issue is to use the Chinese remainder theorem and represent a single modulo Q integer as a two-probe integers in a smaller moduli. So, but recall that capital Q was a product of Q0 and delta to the L, which is not compatible with CRT system. So in our library, we search for L distinct primes, Q1 to the QL, and set the ciphertext modulus as a product of QIs to support this CRT system. So for arithmetic modulo large QL, we just store a two-probe small numbers. Each of them can be stored in 64-bit uint64 variable. And we can do individual small word size operations to represent large precision arithmetic. But the thing is, if we play with the chain of ciphertext moduli, then the rescaling operation at level L basically divides the ciphertext and thereby plaintext by small ql, not by delta. So we can go to only some predetermined ciphertext modulus. So rescaling divide, we can't divide ciphertext by just an arbitrary number, but some predetermined primes in the parameter setting. So if we divide ciphertext by small ql, then plaintext is also divided by ql, meaning that scaling factor is not stable, because we started from two ciphertext with scaling factor delta. After multiplication, scaling factor becomes delta square. But if we rescale this ciphertext by ql, then scaling factor becomes delta square divided by ql, which is different from delta. So there's a ciphertext.scale function in our library, which updates the, so this variable is automatically updated during the computation. We basically keep track of this scaling factor along the computation. In the case of, so in the case of this example, first input ciphertext had a scaling factor 2 to the 40, and after one multiplication, its scaling factor becomes delta prime, which is delta squared divided by Q2. And after one more multiplication, its scaling factor would be delta prime squared divided by Q1. It's again different from delta prime. But the problem is the second term was 0.4 times x, which require only one depth to evaluate. So if we prepare the encryption of second term, 0.4 times x, then we obtain an encryption of 0.4x with scaling factor delta prime. And we should add two ciphertexts with different scales, delta prime and delta 2 prime. And this is not trivial. So a simple solution of solving this issue is just set scale of all ciphertexts as delta bimanually. It is fine because in the parameter setting, excuse me, in the parameter setting, when we search for these intermediate primes from Q1 to QL, we try to make them as close as to the scaling factor delta. So division by QL is approximately equal to division by delta. So it's fine to set the scaling factor as delta. Delta prime and delta prime 2 prime are slightly different from delta, but they are almost close to each other. So you will lose some precision, but it's generally fine. And there is another method which, without precision loss, you can just consume one level to change the scale of ciphertext, but I'm not going to go into details. It's too much. And the precision is another issue we should think about. So basic operations such as homomorphic multiplication or rotation introduce some small noise. So we could say the bit precision of basic operations are log delta minus log noise. And the bit size of noise is usually between 10 to 15 in practical parameter setting. So in our example, log delta was 40. So we could say you preserve roughly 25 to 30 bits of precision after radix point when you encrypt the plain text or perform some arithmetic. Of course, in general case, when you evaluate a complex circuit by representing it as a composition of basic operations, it's generally very difficult to estimate the accuracy of result. You probably need a numerical analysis to make a good estimation for precision. But it's not just an issue of encrypted computation. Even in just plain computation where you use a double precision for calculating some approximate circuit, it's not easy to estimate the precision of a result. So we have almost the same issue here. But of course, you can always increase delta to achieve better precision. And modular switching operation is basically used during linearization or encryption. So there's a special prime, there's an integer called special prime, which is denoted by QL plus 1. And this prime is not for ciphertext, but this is reserved for public key or evaluation keys such as linearization key. So this special prime should be larger than all other primes Qi. Too many is the noise growth of operation. So I'm going to skip some details, but just remember that there's just a special prime, and it is not for ciphertext. And in this example code, the ring dimension n is 2 to the 13. And for the security region, log q L plus 1 should be bounded by 218 to ensure the security. And since we are evaluating the circuit of depth 2, we basically need 4 primes because Q01 base prime Q0 and 2 intermediate primes Q1 and Q2 for rescaling, and the special prime Q3 for modular switching technique. Here, bit size of Q1 and Q2 are 40, so that they are approximately equal to the scaling factor delta 2 to the 40. And Q0 is 60. And Q0 is a 60-bit prime, so that we can decrypt the ciphertext correctly as long as the computation result is smaller than 2 to the 20. So message is always scaled by 2 to the 40. And plain text should be bounded by 2 to the 60, meaning the actual size of message should be bounded by 2 to the 20. But we are just evaluating this simple polynomial on small real numbers, which will definitely be bounded by 2 to the 20. And finally, the special prime Q3 has should have maximal size also 60 bits. And we can double check that the bit size of the largest modulus, the sum of bit size of all small QIs, is 200, which is smaller than 218. So this system is secure. I didn't explain this rotation because rotation is not necessary for polynomial evaluation, but this operation will be used in some later sessions. So suppose that you want to compute something using plain text values located in the different slots. In this case, you can utilize this rotation function to publicly rotate the encrypted plain text and obtain shifted plain text and compute some functions on the values in different plain text slots. And you can check out this another example code. And this is the last slide. And as I mentioned earlier, a ciphertext has a finite level L, and no more computation is allowed when its level becomes 0. So bootstrapping is a public algorithm which generates a high-level ciphertext, encrypting the same plain text. And you can do further computation on this refreshed ciphertext. So it's basically public conversion from level 0 ciphertext to higher level ciphertext. So we can combine this bootstrapping with the leveled CKKS system to obtain fully homomorphic encryption, which supports the evaluation of an arbitrary circuit without limitation of its steps. You can just repeat evaluation and bootstrapping as many as you want. Unfortunately, this CKKS bootstrapping is not yet available in SEO, but we are working on it, so it will be definitely released in a later version in the future, hopefully. Yeah. Okay, thank you for listening.
Are there any questions?
When you rescale, So for the scaling factor, the BGV rescaling just switches the modulus that is in the scaling factor. I guess this, by restricting the limbs to be close to this power of 2, it kind of limits your selection, or your error grows as the number of limbs grows. Is there a way to get the BGV rescaling technique to work with this?
So technically, this rescaling algorithm is almost same as the modular switching technique of BGB or BFE scheme, but the purpose is different. So in the case of BGB, you basically use modular switching operation to reduce the size of noise, but you just preserve the plain text. Here, this rescaling changes the representation of plain text. So as in floating point representation. So ciphertext before rescaling and after rescaling are actually two different encryptions of the same message with different scale.
Okay.
So like okay. Oh. So in this last approximate equality, these two numbers are actually two different representations of the same number. So we divide this significant by a scaling factor 2 to the 5 here to make a trade-off between some efficiency and precision. So, so since CKKS rescaling has this functionality, the goal of this CKKS rescaling is not to manage the noise in ciphertext. We don't care about noise because noise is always a part of plain text. We just consider significant. But the bit size of significant is increased after some multiplication, and we should cut off it. So basically, that's why the ciphertext modulus chain depends on, is related to the functionality of this rescaling in CKKS. So, yeah, so I would say we are already using the same technique to answer your question, but purposes are different. So that's why we have some additional requirement on these primes. So that's why in the original paper, we couldn't use this RNS system because we had to keep this mathematical simplicity. So Q was set to be Q0 times delta to the L to keep the same base. But in later papers, we slightly modified this scheme by searching for some primes approximately equal to delta. So to take advantage of both worlds from engineering optimizations of BGV and still keeping the functionality of CKKS. Yeah.
So for the decryption step, so you just take the like B minus AS mod the ciphertext modulus, and then there's no plaintext modulus that you need to reduce by, is that right?
Yeah, that's a good question. So I didn't clearly explain what is the plaintext space of CKKS. So roughly, the plaintext space is just R, set of any polynomials. But for correct decryption, the size of plaintext should be bounded by ciphertext modulus. So there's no plaintext modulus in this scheme. So you just work on just polynomials with no characteristic. Yeah, but of course, ciphertext itself has modulus Q. So you can recover plaintext by computing C0 plus G1S and take modulus Q. If you generated the ciphertext correctly, then the result would be much smaller than Q in general.
Okay, thank you.
To follow up on the decryption, so the plaintext needs to be smaller than the last Q0, right? Not the full initial big Q.
Yeah, so as computation progresses, the ciphertext modulus decreases, and we don't know how the size of plaintext will change. It depends on input size and circuit, but anyway, the value should be always smaller than ciphertext modulus at lower level to ensure the correctness of evaluation. Yeah, so you're right. So that's why we set Q0 larger than delta, because after consuming all levels of our homomorphic encryption system, you still have a modulus Q0, which is much larger than delta, so that your message scaled by delta would be still smaller than Q0. Of course, we could have overflow could happen because it also happened in plain fixed point arithmetic. So it is important to manage the scale of intermediate values as small as possible, not to have this overflow.
And another question on the intermediate primes, Q1 to QL. So you set them to be equal to the size of the initial scale, right? Approximately.
Yeah.
Is that the best option, or could you also set it in a different way?
So, okay, okay. In general, you can set any chain of moduli. So, because we are going to anyway keep track of the scaling factor following the computation. But the thing is, as you could see in this example of evaluation of cubic polynomial. What's it? Sorry, this is not working. Yeah, so if you want to add some ciphertext with different scales, you may consume one level to perform some one-plane cipher multiplication and let them have the same scaling factor. So we try to avoid this issue and stabilize the scaling factors of ciphertext during computation so that we can just keep almost the same scaling factor delta during the computation. Of course, I'm not sure if there's another better way of setting parameter, but I would say this is so far the best known method of setting. So in the case of, and there are actually more than one libraries implementing the same CKK scheme, but they have some minor differences about this scaling factor. Some of them just don't track the scaling factor, but just set the global scaling factor delta, while our library have this variable ciphertext.scale and update it during the computation. So.
An added comment to that, in Microsoft CO, actually, we generate the prime numbers to be close to a power of 2. So in my example, in my talk, I show that you can pass in the bit size of a prime to set it up. Prime will be generated with that bit size when it's try to get it as close as possible to 2 to the power of 40, for example. So you get the best prime available.
About the, I had 2 questions about, so the scaling factor first, the way to look at it is you explain fixed point, it's 2 to the power minus whatever is the precision. That's the floating part of it, or like the fixed point. So with these QIs, it's effectively, you should interpret as number divided by Q is the actual value. Is that?
Yes, so message is the real value you want to encrypt, and plain text is just it's encoding, encoded message multiplied by scaling factor. So when you really recover your message, you first decrypt the ciphertext and get a plain text and run the decoding function, which include division by scaling factor part. So, yeah. So ciphertext is basically storing significant parts of numbers. Yeah, and it also implicitly stores its scaling factor. So, yeah.
Okay.
Any more questions? All right, let's thanks Yongsoo for the talk, and